Hi everybody. In this video, we're going to go back to talking about differential equations, but instead of just verifying whether an equation is or is not a solution, or looking at a problem and setting up our own differential equation, we're going to have a slightly different goal today. So our goal today is going to be to do two different things. We are going to determine the general solution to a differential equation, and we are going to determine the particular solution to a differential equation. So instead of just checking to see if a solution works or doesn't, we're going to be finding the solutions for ourselves. In order to help you understand this, I want to go back to what it means to solve an equation. So when we solve an equation, we are looking for a particular value of x that makes that equation true. When you first learned how to do this, you started off with really simple equations like the one shown. So if I wanted to solve this equation, I would start by subtracting 4 on both sides, which means I would have 2x equals 6. And then we would divide by 2 on both sides, which means we would have x equals 3. Now, in this unit, we're going to be working on solving differential equations. So I want to show you how these directions mean a slightly different thing than solving a regular equation. When we solve a differential equation, we are looking for the original function that has the given derivative. So a differential equation is going to look like this: dy over dx equals 3x squared. In other words, the derivative of whatever problem you started with, the equation you started with, is 3x squared. Our job is to figure out the original. The process for solving a differential equation is a little bit different than solving an original equation. Than solving an equation like we learned in Algebra 1. So in Algebra 1, when we said solve, we meant get x alone. But the process for solving a differential equation means find the original. So in order to do that, we're going to do three different things. First, we are going to do something called separate the variables. So you'll notice that in this equation, there are y's, like here in the dy, and there are x's, like here in the dx and over here by the 3x squared. Our first step is going to be to separate the variables. Our second step is going to be to integrate on both sides. In the previous unit, we learned that taking a derivative and doing an integral are essentially inverse operations. It's not perfect because there could have been that mysterious constant that we may not know, but a derivative of an and an integral basically are inverse operations. So if we've got a derivative and we want the original, we're going to use an integral to find that. Then we're going to write a plus c. And we're going to do this on one side of the equation only, because whether we had a constant on one side or both sides, they would ultimately get combined into one constant at the end of the problem anyway. And we'll talk more about that as we go. Let's go through these one step at a time. So I'm going to kind of code my work to match the colors. So step 1 is going to be to separate the variables. Oops, that should have an S there. So in order to do that, I'm actually going to multiply by dx on both sides, because the opposite of division is multiplication. And so when I do that, I get dy equals 3x squared times dx. Now that I've done that, I can see the only y in the problem is part of the dy, which is on the left side, and all of the x stuff, the 3x squared and the dx, are both on the right side. The second step is going to be to integrate on both sides. So I'm going to integrate and I'm going to integrate. Now, it might seem weird to integrate if the only thing we can see is a dy. So what I like to do is write in that there's really an invisible 1 here. Anytime that there's nothing times dy, it's always an invisible 1. Now, in order to perform an integral, we're going to do the antiderivative. The antiderivative of the number 1 would just be y. And the reason it's a y is because this is 1 times dy. If this had been 1 times dx, this would have just been an x. And the antiderivative of 3x squared would be x to the third power. The last step is going to be to put a plus c on the right-hand side only. So our final answer here would be y equals x cubed plus c. In other words, what equation would have had this derivative? Well, the original function would have been y equals x cubed. Now we call this a general solution. And the reason that this is called a general solution to a differential equation is because of the plus c. Right now, based on the information we have, we don't have the ability to determine the exact value of c. So we're saving a spot for this mysterious constant that may have been part of the original function. Eventually, on the next page, we're going to learn that with a little extra information, we could actually find the value of c. We could actually determine the specific value. When we do that, we're going to call that solution the particular solution to the differential equation. So this is general. So in general, the original equation would have looked like this. Let's now talk about how to find the particular solution. So on the next page, a general solution, remember we had two targets, find the general solution and find the particular solution. The general solution for a differential equation, it means that our answer should have a plus c in it. This is because we do not have enough information to determine the exact value of c. So we do not have enough information to determine the exact value of c that we would need. The particular solution for a differential equation would be if we have what's called an initial value. Now, an initial value could be any known value from the original function, and we can use that to calculate the specific value of c that applies to this solution. And we call this finding the particular solution. So, a problem in which you could find the particular solution would look like this one. Not only do we have a differential equation, but we've been given an initial value, a value where we know the input and the corresponding output for the original function. Although we already solved this problem on the other page, I want to just walk you through this process one more time. So first, we're going to separate the variables, and the way we're going to do that is we're going to multiply by dx on both sides. When we do that, we get dy equals 3x squared dx. The second step is going to be to integrate on both sides. And remember, if there's nothing next to the dy, there's really an invisible 1. Now, the antiderivative of a number is just the number times the variable. So in this case, that would be a y, which equals the antiderivative of 3x squared would just be x to the third power. And in this third step is where I'm going to put my plus c. So there's my general solution. Now, as a follow-up, so as a fourth step here, I'm going to take this x and this y, and I'm going to substitute them into this equation. So I would have 14 equals, and the x value I'm substituting is 2 cubed plus c. Using now this equation, I can actually find the value of c. So 2 cubed is 8, which means I have 14 equals 8 plus c. And if I subtract 8 on both sides, I get c. I like to think of this as almost like a detour. So we had our general solution. We did a little bit of extra work to find our c. And now as our last step, we can replace the c with a 6. So we get y equals x cubed plus 6. This right here is what we would call the particular solution. Because instead of a c, we were able to determine the exact value that we would have needed to satisfy this differential equation. I'd like to go through a few more examples just to kind of show you some of the different things that you might expect to see, and then we will do some practice problems when I see you again. So let's take a look at number 1 here. Now, number 1 has a couple different things going on. The first thing I want you to notice is that we're going to be finding the general solution. Now, the directions say find the general solution, and it also makes sense that we would be finding the general solution because we do not have the initial value, which is what we would need if we wanted to find the particular solution. So that's the first thing I want you to notice is that we're finding the general solution, which makes sense given that we don't have an initial value. The second thing I want you guys to notice is that we have slightly different variables here. Instead of x's and y's, we have g's and t's. Nothing about this process changes. We're still going to start by separating the variables. So in my opinion, I'm going to start by multiplying by dt on both sides. Now, when I do that, I get dg equals, and I'm going to put a parentheses because it's this entire side of the equation that is being multiplied by dt. I don't want to not put a parentheses because that would make it seem like maybe just the number 5 was being multiplied by dt. The other thing I want you to notice is I'm putting the dt all the way at the end because I know that in proper integral notation, the integral symbol would be at the beginning and the dy, dx, dt, or whatever would be at the end. So I'm making sure that that goes at the end. Now I'm going to integrate on both sides because to undo a derivative, you do an integral. So I would put a 1 here because there's always an invisible 1, which means the antiderivative would just be g equals, and now I have to do antiderivatives. So the antiderivative of secant squared would just be tangent of t. Sorry, just tangent, not tangent squared. Plus the antiderivative of 2t would be t squared, plus the antiderivative of 5 would be 5t, and then I would put a plus c. And this, my friends, would be the general solution to this differential equation because I don't have enough information to go any further. I can't find my c. For problem number 2, I would start it much the same way. So I would start by multiplying by dt on both sides, which means I would have dy equals e to the negative t times dt. Then I would integrate on both sides, and again, there's an invisible 1 here by the dy, which means the antiderivative would just be y. Now, the antiderivative of e to the something would just be e to the something, but what I'm noticing is that there's a little negative here. That means I have to kind of worry about chain rule. It seems like a lot of work to do a u substitution, so I'm just going to kind of use my brain. When I took the derivative of e to the negative t, I would have had a negative as the chain. Like this is like a little negative 1. So I'm going to divide by a negative, which just puts a little negative 1 here. Plus, I'm going to put my c at the end to hold a spot for that missing constant. If we had more information, we might be able to find it and get the particular solution. I'm going to go ahead and save problems 3 and 4. We will talk about those as a warm-up tomorrow in class, and I'd like to move on to finding the particular solution a few times as some practice problems. So in order to find the particular solution to a differential equation, we're going to need more information, and the directions here say find the particular solution. You're also going to notice that they actually give us more information. They give us an initial value. So in problem number 5, I want to find the particular solution, which means at some point in this problem, I'm going to be actually finding my c value. So my step 1 is going to be the same. I'm still going to multiply by dx on both sides in order to separate the variables, which means I'm going to have dy equals cosine of x times dx. Next, I'm going to integrate on both sides. So, since there's a 1 here, an invisible 1, the antiderivative would be y equals, and the antiderivative of cosine is just sine of x plus c. Now I like to call this like kind of taking a detour. Now I'm going to stop and go find my c. I like to draw a line there just to remind myself I'm doing something a little different. In this ordered pair, the x is pi over 2 and the y is 7. So 7 equals sine of pi over 2 plus c. Now, if I think back to my values on my unit circle, the sine of pi over 2 is just 1 plus c, which means if I subtract 1 on both sides, I get 6. Using this 6, I'm going to go ahead and substitute this into my differential equation, which means my final answer for the solution of this differential equation will be y equals sine of x plus 6. That's the particular solution of the differential equation. I'm going to go ahead and save number 6 for a warm-up for tomorrow, and we're going to do number 7 together now. So for number 7, once again, I'm going to start by separating my variables, which means I'm going to multiply by dx on both sides. So I get dy equals, and again, I'm using a parentheses to show that I've multiplied the entire side of the equation by dx. Now I'm going to do an antiderivative, so I'm going to integrate on both sides. There's an invisible 1 here by the y, So I get y equals, in order to do the antiderivative of 1 over e to the x, I like to rewrite this as e to the negative x. Because remember, if your variable has an exponent in the denominator, it's really a negative exponent. Sorry, not if your variable. If your expression has an exponent in the denominator. So this antiderivative would just be e to the negative x. But just like in our previous page of our notes, that little negative would have caused me to multiply by a negative when I originally did the derivative. So now if I divide by that same negative, I just get a negative 1 as the coefficient. Now I'm going to worry about the 2. So the antiderivative of the number 2 would just be 2x, and I'm put my plus c as my placeholder. Now I'm going to use this input and this output to actually solve for the value of c. So negative 4 equals negative 1 e to the 0 plus 2 times 0 plus c. Now, e to the 0 is just 1, so this would just be negative 4 equals negative 1 plus c, which if I add 1 on the other side would give me negative 3. I'm going to go ahead and substitute and replace the c with a negative 3, so I would have y equals negative 1 e to the negative x plus 2x minus 3, and that is my particular solution for my differential equation. All right, thank you guys so much for watching. I hope you have a great afternoon, and I will see you for some practice problems in class.